Welcome back to past paper walkthrough. This is the second part of the GCSE Chemistry paper. So we're on question 4. This is about group 1 elements. Give 2 observations when a small piece of potassium is thrown into water. Well, the first one is it fizzes to form hydrogen gas. Yeah, so that's the first thing. You're also gonna see probably a flame of some kind, and it's gonna be lilac in color. You can also say it explodes. You can say it melts. It can float. It's about it. I think alkaline metals do behave with these properties. You just have to remember the whole lot of things that it does when it comes into contact with water. Now we can do some equation balancing, as we already know that it makes hydrogen gas. So we have that part. And the rest would be potassium hydroxide, which is KOH. To make KOH from that, you need, well, we have one lot of H2, which means that we need extra water to compensate. So we need 2 H2Os because we have OH, right? So there are H here. So total on the right is at least 3, which is cannot be achieved without having 2 water. And to now compensate for the 2 times 2, which is 4 lots of hydrogen on the left, we need 2 lots of KOH, right? And if you look at the oxygen, they add up. So 2 oxygen on the left, 2 oxygen on the right. Potassium, we have 2 on the right, so we need 2 potassium on the left. So that's the whole equation. Alternatively, instead of working this out, you could be very well prepared and just remember this equation from outside the exam hall, which is not recommended, but it is viable. Explain why the reactivity of elements changes going down group 1. There we go. The going down group 1, as we know, let's see, how do I write this? Down group 1, we know that the higher it is, the smaller the elements are, the atoms of the elements are. So we start with lithium, sodium, potassium, and so on, going down. For group 1s, they react by losing the outer electrons, which means the smaller your atom, the closer your outer shell is to the core or the nucleus. The closer it is, the stronger the electrostatic attraction, which means that the less reactive they become, which means that going down increases in reactivity. Excuse my writing. So you need to explain that you have the radius change going down, and you need to talk about electrostatic forces are stronger when when radius is small, right? And then you can then say it's easy to lose outer electron going down the group, and hence it increase in reactivity going down. So you have part 1 of the answer, part 2 of the answer, part 3 of the answer, and part 4 of the answer. That's 4 marks, right? You always guide your answer by the number of marks you're looking for, so always check how many marks you're expecting. Not that you would know for sure where the marks are, but it's a good guideline. Sodium react with oxygen to produce ionic compound sodium oxide dot and cross diagram, right? So you need to start, remember this is a reaction diagram, which means that you need to draw an arrow somewhat. So you need to, I guess, go across. So you start with a sodium. And remember, sodium's got 2 electrons, and then you have 1,8 electron shell followed by, oops, I cannot draw circles, followed by just 1 single electron. And then we have oxygen, which is O, and we have 2 electrons, and then a shell of 6 electrons. Actually, I've made a mistake here already. Dot and cross, probably best to use different electron indicators rather than just cross all the way. Yep. And because it's sodium oxide, we have Na is 1 plus, oxygen is 2 minus, which means that we actually need another Na plus to compensate. So actually we need another sodium. And sodiums use crosses, and that's alright. It's just a bit big of a drawing, this. Okay, so you've got a bunch of electrons, and then now after the arrow you essentially have a bonded structure, which is again the again I need to make sure that I know what indicators I'm using, because now it actually matters. What you want to have is essentially 8 valent electrons, but one of them was robbed, 2 of them for the oxygen is robbed from the sodium, whereas the sodium has now, the 2 sodiums have now lost their outermost valence shell. And in the exam, please try to draw your things a bit more beautifully so that your marker actually knows how to mark your paper. I can do it a bit more sloppily because I'm talking to you right now, but you can talk to your examiners. And remember to remind them of the charges. So this is 1 plus, this is 2 minus, this is 1 plus, yeah? So make sure you have the ion charges in square brackets, because that is the correct indicator. Right. 4.5, why is oxygen described as being reduced? So remember oil rig is reduction is gain of electrons, and we know the O has gained 2 electrons to form O2 minus, which is a reduction reaction, right? So that's why it's reduced. Why the sodium oxide had a high melting point? Now this is a ionic structure question, so it's more like the structure of compounds. So this is giant ionic, and the ionic bonds are strong and takes a lot of energy to break. So that's essentially the 3 marks. So you need to note that it is giant ionic, and then say why the ionic bonds are strong, and therefore it's got a high melting point because the bonds need to break, right? So these are the 3 marks. Question 5, it's about salts. We love salts. Name the salt produced by neutralization HCl, or by hydrochloric acid, with potassium hydroxide, KOH. So we know that neutralization makes water, and if we take H2O out of the equation, we have KCl, which is KCl, and the name of the salt is not KCl, is potassium. Chloride. Potassium chloride is the name, not KCl. I don't know if they would give you marks for KCl, to be honest. I wouldn't, because that's not the name, but maybe I'm harsh. 5.2, write an ionic equation of neutralization HCl with KOH, right? So I kind of already did. Right, okay. Well, this is kind of silly because the potassium and the chloride are just counter ions in this case. So the neutralization is actually just proton plus OH minus goes to H2O, which is simple. Neutralization reactions aren't actually that interesting, but they're very useful, very important in organic synthesis. Soluble salts can be formed by reacting dilute HCl with an insoluble solid. Copper carbonate, and copper oxides are insoluble solids, and which of them can be used to make copper salt? So acid reacts with metal, we know this, and they make hydrogen gas and metal hydroxides. Carbonates also react with acid to make carbon dioxide and water. That's neutralization reaction. And oxides, some oxides can also react with acid to make water and metal. So in this particular case, actually the let's see, the copper itself is in oxidation state 0. The copper carbonate is in oxidation state of copper 1, I believe, is the thermodynamically stable one. Or maybe it's 2, I can't remember. It's both 1 or 2. Copper oxide is probably in 2, so CuO. Copper carbonate is probably Cu2, CO3. Or maybe it's CuCO3. I've never actually used copper carbonate before. I don't think it's that useful. But that's my sidetrack. Copper itself isn't very reactive. And if you use really, really, really strong acid, it will react with copper to make your hydrogen gas and copper hydroxide, but we're using dilute hydrochloric acid, so that's actually not very viable. Copper carbonate is a weak base and it definitely reacts with hydrochloric acid. The copper oxide, again, this is kind of an edge case. I would say it probably would react with hydrochloric acid, but it depends on what you've been taught. I think this question is a bit harsh for GCSE grade, and I would say this is the right answer. Yeah, I mean, if we've ruled out copper as a valid option, then it essentially killed these 3 answers anyway, so there's only 1 correct answer. But to be honest, it's kind of rude, this question, I find, unless it's in the syllabus, which I probably should know, but I don't. Anyway, we're making MAC sulfate. This is the method. Sulfuric acid, warm it up, add a spatula of magnesium oxide, stir the mixture, repeat 3 to 4 until until we consume all the sulfuric acid, basically, and then filter off the mixture, evaporate the solution until crystal form, and then leave it to crystallize. So we need to give reasons for question step 2, step 5, and step 6. Right, so step 2, why are we heating the sulfuric acid? So a hot solution dissolves more salts. Magnesium oxide is a salt, right? So you want to dissolve more mag oxide into the sulfuric acid. So high T increases of magnesium oxide. So write it in words if you can in the exam, but I'm just gonna, because I'm talking through it, I'm just gonna write shorthand. Step 5 is repeat 3 and 4 until there are excess magnesium oxide. So you want to so you want to consume all sulfuric acid to reduce impurities. That's one of the answers. There are many answers to every single step here because, well, you want to give it time to react, and it takes some time for mag oxide to go into sulfuric acid solution. And if you don't repeat 3 and 4, or if you don't stir, not all of them will dissolve. And if you don't add more magnesium oxide after everything's dissolved, you don't know if there are still sulfuric acid left. And excess sulfuric acid is harder to clean up than excess magnesium oxide, which is also the reason of step 6 is to remove solid impurity in the form of magnesium oxide, right? So magnesium oxide is a solid, and sulfuric acid is not a solid, it's a liquid, which means that if you have excess sulfuric acid, you need to like distill it off essentially, and it's not actually going to work in this case because we need to wait for it to evaporate and crystallize. Whereas if you have excess magnesium oxide, you can filter off the solution and get pure mag sulfate solution, which you can then crystallize. Right, how should the filtrate be evaporated gently in step 7? I think if I were doing it, I would just leave it on the windowsill. Oh wait, no, you need to do it until the crystals start to form. So normally this is when step 8 is when you want to leave it on the windowsill. If we evaporate the filtrate gently until crystals start to form, we need to start a nucleation of a crystal. So you need to start growing the crystal. So you probably want to warm it up with like a warm water bath. It's probably fine. Electric heater is fine. Hair dryer is fine. There are a lot of different options here. It's only one mark. Any one reasonable heating option is fine. Don't say blow on it or like rub your hands on it or something silly like that. That's not very efficient. Right, iron chloride is produced by reacting iron and chlorine gas. And now we're calculating. This is a lot of math. Oh dear. Well, guess it's time for me to do some math. Haven't done math in a long time. Calculate the volume of chlorine needed to react 14 grams of iron. So iron is AR of 56, so we need to find the number of moles we have, which is 14 divided by 56 is the number of moles. And again, using my trusty calculator, we have 14 divided by 56 give us, exactly 1/4. I don't need a calculator for this. So 0.25 moles of iron, which means that for us to react, we need to find the stoichiometric ratio. In this case, this is 2 lots of iron for 3 lots of chlorine gas. And 2 lots of iron and 3, if we want to use that ratio, we need to calculate the mole of chlorine gas is 0.25 divided by 2, which gives us 1 unit of iron times 3 unit of chlorine gas, which is 0.375 mole of chlorine gas. And we need to find Oh, actually, it even tells you how to do this question. That's very easy for you. So we have the number of mole of iron, which is the 0.25. The number of chlorine used is 0.375, and the volume of chlorine we need to use. Well, we don't even need to use ideal gas. It's given to you. 1 mole is 24 decimeter cube, and your answer is in decimeter cube. There are literally no traps in this question. So we have that amount of moles, so 24 dm cube times 0.375 moles is, actually this is per mole, isn't it? So that would give us 9 dm cube of chlorine gas. So this is 9 liters of chlorine gas, which is a lot. That's a lot of chlorine gas. You do not want to get anywhere near that. Question 6, we have a bunch of melting points and boiling points. Which substance could be a metal? Melting point should be high, so it's not A. Metals don't melt at negative temperature. Metal conduct electricity in the solid state, so it is C actually. That's indicative. Okay, this is a bit too easy. I think this might be a trap. I don't know. It's probably not a trap, but it feels too easy for me. Explain why alloys are harder than pure metals. So pure metals have regular lattice structure, right? And alloys, alloys have disrupted lattice structure, and therefore the metal layers or atom layers can not easily slide past each other, right? So that's why they have a harder texture essentially. And alloys are made of different elements. And different element has different atomic size. So they pack differently. So it's about close packing, right? So you've got I don't know if it's in the syllabus or not, but you've got close pack, hexagonal close pack, you've got square, cuboid close pack. Those type of different close packing will be disrupted by different sizes of atoms, and that would affect the hardness. But we're chemists, not materials chemists or material scientists, so we don't talk about those in the correct terminologies, which I probably should, because I used to be half a material chemist, I guess. But anyway, question 6.3 is, do not compare reactivity on non-metal Q with zinc both are more reactive than sulfur. Okay. Describe a method we can compare reactivity. Your method should give valid results. Okay, so this is a reaction kind of design type question. And let's see. So essentially, the given thermometer is a big indicator of what you should be doing is try to do calorimetry type. So reactions are mostly exothermic, which means that you can measure the exothermic properties of the reaction between zinc and sulfur versus Q and sulfur, right? So the more reactive a metal is, the more likely it's going to react with the nitrate, and it will reduce the sulfur 1 into sulfur 0, which is a sulfur mirror reaction. So what you need to do is to, I guess I'm not going to write, I'm just going to talk, just note down what I say here. You want to do calorimetry, and you want to weigh out the same number of mole or same amount of mass of, hang on, actually no, that's a mistake. No, you want to use excess metal, and you want to use a known amount of sulfur nitrate. So you want to use a standard sulfur nitrate solution, say 1 molar, 1 molar sulfur nitrate, and you want to know exactly, you use exactly the same amount of volume for both reactions. You want an excess amount of metal. So what you do is you add the excess metal into the sulfur nitrate solution, stir it, and then measure the temperature change. So you should have the initial temperature at room temperature, and then after addition of the metal you should get a temperature time graph. And what it would essentially look like is it would look something like that, and you'd have a flat baseline, and then once you added your metal at this point, the temperature would creep up, and then after it creep up to the maximum, it will start going down steadily at room temperature, room temperature decay, cooling. So what you can do here is to elongate the standard steady state temperature, backtrace your decay temperature, and then find on the addition time, find this delta T. So this is the true temperature change of the reaction, which gets rid of the thermal loss to the environment. You probably have done this calorimetry experiment before in a lab, hopefully. And if you haven't done that before, you should have learned it before. And so you can use E equals to mc theta, or some type of those equation. I think there's also mc delta T, is it? They are the same equation, by the way. So that's to find the enthalpy change of this reaction, and you can use that to calculate the difference in delta T, and you can hence infer the difference of reactivity of the two metals. So that's the way you would get around this, or go about doing this question. But it's just a basic reactivity kind of experiments. Also, it's quite, I suppose it's quite hard. So it's 4 marks. If any fair attempts on measuring the temperature or doing a standard solution or a same mass, same mole, any of those would give you 1 mark. And any fair try on describing a calorimetry experiment would give you a pretty good a few marks at least. So yeah, at this point we have hit another 36-minute mark, so I probably should stop here and we'll get on with the last bit in the next video. Hope you've enjoyed and you've learned something, and if you have any questions, do let me know in the comments below, and I will see you next time.